here we go.
Correct. Thanks, Andreas. So, as you might notice, I'm at the right age to talk about history of things. I have the license to do that. I thought it's a good idea maybe to wrap up the history of media networking and to draw a conclusion about have we reached our targets, actually. And so, how did we get where we are today with networking, and what have been actually the expectations? What is the status, what are the problems, and what are possible paths for achieving convergence? So, shortly about me, since 2004, I've been running very intense market research about media networking. I've done more than 500 interviews in total with people working in theaters, sound engineers, rental companies, consultants, venue operators, and so on, you name it. I was responsible for product planning at Yamaha, professional. I did product management at Riedel for Rocknet and MediaNet, and I have been head of market intelligence at D&B for 9 years. So I thought let's scroll back in history and see how it all happened. Yeah. So in the 1980s, the first devices with digital audio processing came up. And the first ones, they really were problem solvers. They did things that were impossible to do before, like reverbs. So we had these famous machines like this one, Quantec Raumsimulator, one of the first state-of-the-art reverb machines. And please notice, are you okay, team? Please notice the interfaces. These machines, they were all like analog in, analog out, and a little bit of remote control here, which is probably for a foot switch or something like that. Yeah. And then there were also cheaper versions of this. Dynacord was very busy at that time, very much ahead. And now, apart from all the analog interfaces, we already have MIDI ports here for controlling the device. So you could at least recall a preset or change some parameters or do some things like this. Yeah. Now, in the 90s, the first digital mixing consoles came up. O2R was a very important product here, and it introduced some new concepts, especially the card slots. So they could be filled with different cards, as you may know, for different audio standards like AES-EVU, analog, or whatever might come in the future. It was very important for making buying decisions at that time to be super flexible. But notice the control side of it. Again, we find the MIDI ports. And here's a little one. It's like a keyboard connector. And it says 2 hosts, so you could control the device here. Yeah, timecode inputs, and so on. And it was the time of digital controlled analog devices. So there were these famous things like Midas XL4, BSS Varicurve. They had an analog audio path, but the parameters, some or even most or all of them, were controlled by a digital logic. And we have very nice equipment, but very expensive. They produced a lot of heat. And yeah. Okay. In the 2000s, finally, digital mixing became more or less a commodity. After PM1D was introduced 2001, PM5D became one of the most sold consoles ever in our industry. And look at the rear. So I only took a photo of the main part, the master part, but we have GPI for control, we have RS422, we have head and special connector for head and remote, we have MIDI, and we have a USB connector. So it's a nice chaos of control connectivity at that time, and quite complicated to make a system actually work with this. And look what happened 1 year later. This was Yamaha M7CL. Bang, finally we find this little RG45 socket here. Ethernet was introduced as a remote control for devices. And it was pressure from the market, actually, because it was becoming very, very difficult to feed all these different interfaces from computers. And Ethernet was seen as more easy, and it could also be networked over a distance, which was very hard with a serial or with USB and these kind of things. At roughly the same time, a revolution happened in amplification, which was that amplifiers now hosted DSP. And one of a famous system was from Electro Voice. Actually, the amplifiers were produced by Dynacord, but they had DSP inside, and this DSP could only be remote controlled via these connectors, and CAN bus was very important at that time. It was used for this. Alternatively, there was an RS-232, yeah, and of course GPIO connections. And DNB, by the way, went a similar path with CAN bus connectors. They look like Ethernet. It's also an RG45, I think, but it's not Ethernet. It's CAN as a protocol. Yamaha at that time was pretty advanced, I would say. They already published and actually sold a system for controlling a whole amplifier network via CobraNet. And the important requirement at that time, and really the need in the market was, can we have please only one cable? That was the key thing, yeah. And this cable was requested to carry audio and control to the amplifiers. Key thing. Now, I believe the whole debate about signal and control infrastructure changed when amplifiers became digital. So here's an example. This is a K6 PowerSoft. This is a PCM amplifier, and this means that the signal path inside the amplifier is not analog any longer. The analog filter is at the output of the amplifier. So now it became critical to feed this amplifier with a digital signal, because then you could make a whole digital signal path from your console up to the loudspeaker, more or less, yeah? And it was a very important paradigm to only have one cable for this. This is why PowerSoft designed something very weird. It was called AZOB. And AZOB is an RG45. It's actually standard Ethernet that could also pass a switch, but it also carried AES3 streams on top. Very strange solution. But it was a response to the very urgent market request, can we please have only one cable here? We don't want two cables. Yeah? It's too complicated. We don't want that. So what was the situation like at that time, roughly 2010, 2015? Ethernet became the dominant interface for software-based device control. And amplifiers became digital, and they hosted the speaker DSP, and this made it necessary to control them with the software remotely. There was no other way to manage the system. And the entire audio path from mixer to loudspeaker actually became digital. So many devices in the system now require very extensive remote control and digital audio signals. And system complexity at that time really became a huge topic. It was very stressful to build something and make it work. So the idea of fully digital system became very urgent and very tangible also. And so there was a market need and a vision for change. And the big question was coming up, hey, now we are networking all our devices with Ethernet in order to control them. Why couldn't we also have the audio on that Ethernet? Yeah? It would save us a lot of work. We would just have one network and it would do the whole job. That was kind of the starting point. Couldn't all devices in a system share this common Ethernet, and then they could even talk to each other? And this was seen as a simplification, as a big simplification compared to the chaotic status before. So people wanted to get rid of the chaos. And this was seen as the one road to total and easy interoperability. It was like, now our dreams are coming true. So the expectation at that time, thinking about Ethernet as a network carrying control and media, was clearly for a converged network, one network, doing both jobs. If you at that time had told people, no, you will need 2 network connectors for your device, they would have said, I don't want that. Stay away. We don't want that. So the whole idea was it could be one. But the early days, we all had to learn a lot about networking, including guys like me. We had to learn how does this work. So the key question was, is it practically possible to use legacy Ethernet as a network carrying real-time media traffic and control data on one cable without trouble? That was kind of the major question in the room. Is this possible? And now there are different answers, and there were different answers to that question. The first answer came from IEEE. And IEEE is kind of the mothership of Ethernet. It's the place where Ethernet is defined in standards for layer 1 and layer 2. And the answer from the IEEE guys was no, don't do that. They said diffserv, quality of service, will not provide the desired determinism and reliability. Such a network will become complicated to manage, still not 100% reliable, and different types of traffic need to be separated. Multicast is another problem. So in order to do this, you will need a new type of Ethernet, and we call that AVB. That was kind of the trigger to upgrade Ethernet to actually do this job. And that's what ABB actually is. A different answer came from Ordinate. So we had Dante conquering the market, and they were clearly saying, yes, you can do that. Yeah. You can use standard Ethernet switches off the shelf, and you can combine control and audio on one cable, and it will work without hassle. And I have to say that most people, they were totally fascinated by this approach and by this proposal, and they went for that. And in the beginning, of course, the systems were very small. It was more like point-to-point or few devices networked together, and that worked very well. But nobody at that time really envisioned what this would mean if the system would become larger and if there was different type of traffic on the same network. And then there was a third answer, because in the meantime, we also had proprietary networks coming up, not using Ethernet, but time division multiplexing, like StageTech Nexus, Optocore, Studer, Lavo. They were all working on these things, RockNet, MediaNet. Yeah? This has nothing to do with Ethernet, and it's clearly made for audio or video in case of MediaNet. And the answer from these guys was Ethernet cannot do that job, and it will never really be reliable and easy enough. You better use something that is made for audio, dedicated, and this will make your life easier and less stressful. So there were these three approaches in parallel, so to say, in the big discussion space of pro audio industry. And let me summarize that into a picture. So we had these urgent needs for controllability of devices, roughly in the 90s, and digital audio connectivity coming up. Then later, Ethernet becoming standard for device control. Audio was still separate and on various standards like analog and AES3 and MADI and these things. And the system structures were pretty chaotic. And then there was this question, can legacy Ethernet be the one network for audio and control? And we have this one answer here from Dante. Yes, Dante is based on PTP version 1. We had the answer from the IEEE guys saying no, and this kind of triggered what I would call the first AVB hype. There were companies relying on this IEEE approach saying, okay, then let's go that way. And they did some mistakes, I would say, because many companies implemented AVB in different ways, and they were not interoperable. And this led to a quite chaotic situation in the market. And then we had the TDM guys still saying, oh, no, we don't want to get into this, use our dedicated proprietary stuff in order to build networks. And then over time, when the first problems with Dante occurred, and people noticed that the precision of PDP version 1 might not be sufficient, and there are lots of other problems, and also the switching technology improved, so we had new PTP standards. PTP version 2 came up, much, much more precise than PDP version 1. So there was a new camp coming up here saying, yes, you can use Ethernet, but it requires a better transport and PTP in order to work well. So, and this was where QLAN was born on, and Ravenna, ST2110 later, and all these kind of things. In 2018, Milan was launched. So this was, we may want to call this second generation AVB. And it added an interoperability specification to the original AVB to make things guaranteed, interoperable, and certified. And this is what Milan is up until today, still developing with lots of details and features. And of course, there are still some older AVB devices in the market that don't relate on the same interoperability spec here. So what is the modern need now for network convergence? Because the situation, as you can see, has become pretty weird. I mean, we have different network standards out there. So we have many different protocols, and they must be supported. And it isn't as simple as we thought back in 2010 and 2015. At that time, we really thought, hey, yeah, let's go for Ethernet. Wow, we will have one network, and it will do the job. And the reality is that we are now looking at a situation like this. What we actually want is one network, and this network has to carry Dante, Ravenna, QLAN, AES67, Milan, TCP/IP, and please add ST2110 here, or IPMX, or NDI, or whatever video. So if you today design a system for a building, for an installation, or even for a large concert, this is the requirement. You will need this. Yeah? Maybe not all of them at the same time, but a lot of them. And converged would mean it's one network. Yeah? And of course, we have a local network management. We have our control software to make the connections, set the sample rates, and do all these kind of things. But more and more, we also need remote network management. We need cloud services to be able to look at the network and to help the user on site with certain services about the status. Yeah? So what we're actually doing in such a converged network, and we are merging IT and OT. So we are merging generic control based on TCP/IP, or it could even be a printer or a computer or whatever network you use. We are merging this on one network with our very, very critical audio and video streaming, which in case of live productions is very critical. It's not allowed to be interrupted in any form. So now, what is the status like? The promise originally was for convergence and simplicity, one network for all devices. This was the promise made by manufacturers. Dante requires strict separation from generic best effort traffic in the network. So only dedicated, limited amount of control traffic can coexist on the same port. So most Dante devices actually have two network interfaces. One is for controlling the device, and the other ones, the two here, are the primary and the secondary Dante port. Whenever devices mix that together in one network, there are many customers who refuse these devices because they know by experience that if this network is the same as the one where I have my TCP/IP control for the rest of my system on, it's gonna end in trouble. You know? The next problem is that PTP version 1 and PTP version 2 are not fully compatible. So it's not very easy to have them both running on a network. You really have to carefully pick your switch and check if it works or if it doesn't. This is a very difficult matter to deal with. It requires certain care, and this is the most useful practice or the most often done way to do it, separate. So we very often see that people separate networks. This is my Dante network, and this is my other network. These kind of things. So again, another non-convergence, the opposite of what we wanted to achieve. Then again, QoS, so diffserv, only provides a relative prioritization between types of traffic. It cannot really guarantee that a certain packet will arrive in a certain time at the receiver. But the loudspeaker system, especially the loudspeaker systems, they require not only high reliability, they also require an extremely high precision in synchronicity. So if you drive a line array and each element is a network node, the precision in timing we need for the arrival of the signals must be better than 1 microsecond. There's an AES paper on this if you're interested. This has been examined in depth, and yeah. So I would say, I would like to make some statements here. In most network ProAV systems, different types of traffic these days must be separated for technical reasons, just for the reason that it doesn't really work. So we haven't really achieved the convergence. Second, many people try to do this by VLANs. They believe, I just configure some VLANs and then it's separate and nothing can happen. You will still have traffic collisions on the trunk lanes between your switches, and they are pretty hard to manage. My colleague Bart Swinnen will have a presentation after this one touching this topic and presenting a possible solution to this. And in reality, it looks like that many systems out there, especially in live productions, they base on a number of physically separated networks. So we see many tours or large festivals where there are 2, 3, 4 parallel physically separated Dante networks. Then there might be a video network and another network for IT and control and these kind of things. So this hasn't become more simple, it has become more complicated. And what I hear a lot from integrators, especially, because I interview these people on these topics and I ask them, hey, how does this work for you? They say very often systems have become too complex for the users. So very often the network must be locked away from the users. If the users start adding a device or changing something in the network, the risk that the network crashes is big. So that's why network has actually become a risk. And having said that, we haven't even touched the real problems. So most users, if we imagine that we have just one network for our whole system, this is also a risk because it makes people very nervous that there are many different users having access to all the devices in the network. So back in 2015, roughly at that time, most people in the market were imagining, oh, the network guys, they will solve the technical stuff. They will make it work. The network will just work, But this is really critical. How do I protect my devices in the network against being tampered with by another guy in the same network? How does that work? How is that managed? So how can we allow certain interaction between devices while blocking other and so on? So these questions are most relevant to real users and especially to those who are responsible for productions. And it's a big topic, but as long as we haven't even achieved the convergence technically, this kind of is a second problem behind our current technical problem. it's another topic for another day. Stay tuned. There will be some suggestions for this coming. So how could we actually achieve convergence? I currently see three trends. Manufacturers are launching special pre-configured Ethernet switches in order to overcome the difficulties for the users to configure switches. One example is Yamaha. Yeah, they have special switches pre-configured for Dante, making the life easier for the Dante users. Yeah. This, of course, has a limited acceptance. The other path is you can hire a specialized expert to build your network. We have people, there are also people in this room who are really good in this, but it's, of course, not an approach that goes wide into the market for the everyday's application. And the third path is AVB. Still, it's the new Ethernet technology that provides guaranteed delivery at guaranteed time. And I briefly want to highlight the convergence toolbox of AVB. So in legacy Ethernet, when you think of a certain link bandwidth between 0 and 100%, any type of data can consume the entire bandwidth. There is no traffic shaping, and the bandwidth is not kind of spread across different types of traffic. So whatever you put on the network, it could be anywhere here. And then the QoS introduces some priority and says, okay, we want the highest priority for the PDP timestamps, and then for the media streams, and then for the device control, and so on. But again, this is only relative. It cannot guarantee the arrival. AVB works completely different in this regard, at least. We have a defined space for media traffic, and this goes up to 75%. That's a value that can be configured, and the rest remains for other traffic. So here the picture looks like this. Yeah, we have our best effort control traffic, device control, and non-AVB audio data living up here. The PDP timestamps of AVB, they have a special transport layer anyway. And then below here, we have all the AVB traffic living in its own space in reserved streams. And this makes it possible that you actually have your device control and your audio or your video on one cable without any interaction or disturbances. Yeah? And one thing is important to point out, this value here, 75%, is a dynamic range. So as long as you don't use AVB streams, you have the full bandwidth available for all your control traffic or whatever you want to use your network for. Only when you start using AVB, it starts filling up this space until this border. And this is a feature, this is not a problem. It's a great feature because in the legacy Ethernet, you don't have this. Everything could, in theory, require the entire bandwidth. I think I'm a little bit out of time. So one thing just to point out, since we have AVB in the market, and we're glad to see that it's quite successful, devices look like this. So this is a redundant Milan interface on an amplifier, two Ethernet ports, primary and secondary. And on this port, we carry the media and the control without any trouble, any interference. But on the same network, you could have your IT. You could have your printers, whatever. You don't have to worry, it works. Yeah? And this is already a reality since some years. So this type of system is actually being used on all of the productions you see here already, with a failure rate of, as far as I know, 0 so far, and very, very enthusiastic and satisfied customers. And with this, I would like to hand over to Bart, taking over the more technical, deeper dive into what's actually going on here. Thanks.
Right. Thank you, Henning.